Hello everyone, my name is Andrei and today I want to make a tutorial in which we will create a complex pattern, and for this we are going to use a advanced simulation. For this reason I will briefly talk about partial differential equations, how to solve them, but more importantly how to think about them. So partial differential equations can be used to describe different phenomena we observe in nature, like the weather, fluid dynamics, disease modeling, and so on. However, while we will approach some of the math involved, we will actually focus more on how to think about these topics like an artist. Okay, so what partial differential equations look like? Well, they look like this, and this can be a little bit intimidating. I found this system of partial differential equations in a very nice book. If I remember correctly, the book is called The Algorithmic Beauty of Seashells. In this book you will find many similar system of partial differential equations, and these systems describe how the patterns of pigment form on the surface of seashells. How to interpret or how to read these equations? Well, basically this equation says, the first equation says the derivative of A with respect to time is this expression. And I want from this point forward to think about that we are going to create a movie in Substance Designer, okay? And in this case, A is the first frame of the movie. And this is considered to be, or it's equivalent to the initial conditions. So our movie starts with the first frame and it's going to evolve in time by following this mathematical operation. Okay, so our first frame is an image. It can be anything, like for example the Berlin noise or a white noise or a pyramid or a disc or anything like that. And in order to compute or to find the next frame, we need to perform this computation. Okay, and just want to say that in order to get from the first frame to the next frame, we need to measure somehow the first frame, add, subtract, multiply and divide a bunch of things to it, and we're going to get the next frame. And critically, what makes this a differential equation is that we are going to involve the derivative or our current state. So the derivative is just better to think of it like a measurement of our current state, of our first frame. Okay, so you can think like this: the first frame of the movie is going to be measured, and based on this measurement and some other mathematical operations, addition, division, subtraction, and so on, we're going to get the next frame. But the next frame is going to be related or proportional to the first frame because we measured it. So we are growing or finding the next frame based on a measurement of the current frame. Okay, so what I also want to add is that this expression here, you have a lot of symbols, and those symbols are sometimes, for example, A is an image, is the current state. For example, the current state is multiplied with itself, and then divided by b. What is b? B is this second initial condition that we have because we have like two equations. BA is a number, RA is a number, DA is a number. This expression here is the second derivative, or the measurement of our current state. So then if we just add, multiply, and do all the math, we are going to get the next frame. And the crucial idea to remember here is that in order to compute the next frame, you're taking the current frame, you measure it, and you add a bunch, you add, subtract, multiply, and do some other operation with a bunch of numbers and get the next frame. So this is it and nothing more, and this is the way in which we're going to think about solving this system of equations. Okay. Now, how to solve differential equations? I'm going to very briefly talk about the way in which these things are solved. So they can be solved analytically or numerically, and depending on the difficulty of the equation that we want to solve, we might be able to solve it analytically or numerically. Now, ideally, and if possible, we would want to solve these differential equations analytically. This way of solving them is very precise, very fast to compute, but in many cases it's very difficult to solve them or impossible. And for these reasons, we have another way of solving them, which is solving them numerically. And the numerical way in which we're going to solve differential equations is called forward Euler. And forward Euler is exactly what I described. So we're taking the current frame and we want to find the next frame by measuring the current frame and adding and subtracting and multiplying a bunch of stuff to it. And this is how we're going to get the next frame. And then we're taking the next frame, measure it, add, subtract, multiply the same bunch of stuff and get the third frame or the second frame, and so on. So we repeat this repeat this process until we push this system forward in time how far we want. And I also want to mention that this kind of process is giving rise to very rich and natural looking and complex patterns. And what is going to even more contribute to this complexity is involving two very crucial processes. So the first process that we are going to involve is called feedback loop or iterative function. So we're going to repeat over and over the same computation, and the result of this computation is we're going to take the result of this computation and bring it back into the equation and do again the same computation with it. And now the current result, we're going to take it back and feed it back in, and this is the feedback loop. So this is one crucial process that gives rise to very complex patterns. And the second process that even more contribute to complexity, and it produces what it's called emergence. So from very simple system, you can have in certain conditions very complex patterns and behavior that emerge from simple system. And this second process is called coupling. So you're basically mixing two systems together. So maybe it's not visible right away, but this system of equations is coupled. So for example, you need to solve this simultaneously. So for example, you can see that B, the system, the initial state B appears in A. So A not only depends on itself, but also depends on B. And B also depends on A. So those equations are crossing each other in some way. And this mixing or this coupling between the two systems of equations is giving rise to very high complexity patterns. So you can think of this in the following way. Like one example that I can think of is that you're a student in your class and your behavior is shaping the dynamics of the class and how you get along with your colleagues and with your teachers. But also they as a whole and as a group act on yourself and they change your behavior, and then you adapt and then you behave in a different way and they react to your new behavior and they change, and they again based on the how they change, they are going to influence you once more. And this is like the feedback loop, and this is the interaction between two systems. It's how you as an individual interact with another system, and from this coupling of things usually results or emerges complexity. And I want to illustrate this with the system that we're going, or with the simulation that we're going to create today. And we're going to start with an initial frame, and we can think of this like, hey, this is a creature that lives in this space and it wants to eat other creatures. So it's going to sense its environment, and if it's going to identify some smaller creatures nearby, this large creature is going to evolve and grow in that direction, trying to capture the smaller creature and eat them. And then you have a bunch of smaller creatures populating this space, and those creatures are actually going to look around and try to protect themselves. So if they see the large creature coming to eat them, those smaller creatures are going to try and escape, so they're going to run away. And I want to actually show you what's going to happen. So this is our initial state of our large creature populating the space or sitting by itself in this space, and then this is the initial state of our tiny creatures. And after a number of frames, our large creature is going to extend in such a way, chasing the smaller creatures, and the smaller creatures are actually going to move out of the way and they try to run and escape. So we're going to continue this process, and you can see like our big creature is going to grow even more, and our tiny creature are going to again try to run, and this system continues until everything evolves like this. And what you can see is that this pattern is looking natural. So the thing that I like about it is the kind of natural quality that it has, and also I really like how we're getting this branching out of it. Okay, so you could also export this as a movie, and I'm going to depending on how long this tutorial is going to be, I might actually show you how to export a movie out of this. Okay, and before actually, so we're going to recreate this from absolute scratch, and you're going to see some really interesting techniques. We're going to use pixel processor, the NFX map, and just to make sure that I don't forget to mention this idea, what I wanted to say with this system is that we have like two individual systems interacting with each other, and that's what is producing complexity. So the first system is the large creature is trying to eat, and it's chasing small creatures, but the small creatures also react to the large creature. So whenever the large creature is getting too close to the small creatures, the small creatures actually start to run. And now the large creature is chasing the small creatures, and the small creatures are actually running away from the large creature, and this cycle repeats itself, and that's what is creating this type of patterns where we're getting branches and curves and things like that. So we never specified any trajectory for this for these tiny creatures, and still we have like branching paths, and you can see that they are curving and twisting and stuff like this. Okay, I also want to show you similar systems that can produce other types of patterns, which can be very interesting. So I really like, for example, this stuff here. This is almost exactly implemented the system of equations, and I'm going to show you how I implemented them. So for example, this is the initial state A. This is this thing here, or this thing here. This is A. This is how I started, and this is B. So I choose A and B to be white noise, and this is a regular white noise, and this is the same white noise, but I changed the seed to be 12. And then we go ahead and actually create these two equations. I will go inside this, and we have like 64 frames, and you will actually, I'm going to double click on every single frame. So this is the first frame, second frame, third frame, fourth, and so on, and you can actually see it how it's evolving like a movie. Okay, and this one is how we compute a frame of our movie. Going inside, and you can see we have two equations, and this equation is exactly replicating the math functions or the math operations that are written here in the equation. And I want to actually show you, for example, how a squared looks like. So if you remember, a is this image, and in order to compute a squared, what we do inside the pixel processor is I'm sampling the image. So this is bringing the white noise inside the pixel processor and then multiply it by itself. Okay, so this is a squared, and now you see we divide a square by b. Okay, so going back here, you can see b is the second image. Going inside, this is b. I'm putting b as image input 1. So image input 1, this is b. So a squared divided by b. And up to this point, we implemented this fraction here. And we're going to add to this fraction ba. BA it's a number. So in this case I decided not to use BA. It could make a difference, but whenever you have a constant like this, like a single number, sometimes you can just ignore this and not use it. So what I would suggest is initially you just go and implement the equation exactly as it is, and then what you would actually do is just play with a lot of values and change. For example, whenever you have like a constant like s is a number, it can be 0.5, so you would change it like 0.51 or 0.55, and depending on the results that you're getting, you are going to save and keep these values. And if you want, for example, you can skip and not use constants, and if you still like the result that you're getting, you can just go find with that. Okay. And what I wanted to say again is that all these frames here, it's the same set of instructions, so the same mathematical operations are exactly the same in every frame. What is changing is the input. And remember, this is how we're doing the feedback loop. So we're saying that we're taking the first initial condition and we compute the next frame, and then this is becoming the initial conditions, and we are putting this inside and we're computing the next frame. So in Substance Designer we can't take this input and plug it back in here. That would be cool if possible, but doing it like so in a sequence of node, it's exactly the same thing like taking this and plug it in back, but we can't do that, so we need to create every single frame. So if we were, for example, to export these frames as a movie, you would have a sequence of images that you can plug it or bring in After Effects and actually get you could create a movie. Okay. And I really like for example, from those equations, and we start with noise, you're getting an emergent pattern. This is, for example, looking like maybe like a cloud formation. I always have like Jupiter atmosphere vibes when I'm looking at this. So again, the same system of partial differential equations, and you're getting like a different pattern. So for example, changing the values of the parameters inside inside of these frames is going to change how your pattern looks. And be careful, because those systems are very, very sensitive to the changes in values. Like a small change in these values can give you like wildly different results. And you also can notice that it is fairly arbitrarily slow to compute because we are doing a lot of iterations. So Substance Designer, it's actually computing these things as fast as it can, which is still very responsive. So I think we're getting like a half a second to compute this, and we're having like 64 frames multiplied by maybe 13. So I think we're having around maybe 800, 900 frames, and computing them in like half a second. I think it's fast enough. Okay, let me show you one more pattern before we actually start to create things. So for example, I really like this kind of pattern, and I want to show you that we can start differently. In this case, we are starting with points like this, and we're growing them in such a way that looks interesting. And what I like is the way in which those waves interact with each other, and I think this pattern looks really decorative. And you can go, the nice thing about this is because everything here is the same equation. So if you change one thing inside of every node, is changing this thing inside every other node. Going here, and we can change the histogram here position, so you're getting this kind of pattern. Okay, and the changes that you're making inside this node actually propagates to every other node, so you're making the same change in every other node. So changing the value of the blur here, it's actually making these things rectangular. Before they were round, now they are rectangular. Maybe we can increase this. So now we change this, and instead of having circles, we're having something polygonal right now. I'm going to hit undo a few times to return to the pattern. Okay, so yeah, this was a long introduction, but right now we're going to go back in to our advanced simulation, and we're going to try and recreate it from scratch. So I will just duplicate this part here and rebuild everything else step by step. So in this case, this is our creature, and this is our first initial condition. And then I want to show you an interesting technique when we are going to work with data in Substance Designer. So we're going to create a list of values, a list of vectors, and every pixel in this list, it's a 2D position. And we're getting this by taking a white noise. And how I did this, so white noise fast, by default you're getting a 1K texture, or depending on your settings, you're going to get something depending on what you set up here. And I want to make this smaller, so output size is going to be absolute. I want this to be width of 256 pixels, but I want just one row. So for example, if I'm going to put here like 4, we're getting 16 pixels, 3 8 pixels, 2 4 pixels, 1 2 pixels, and then 0, we're getting 1 pixel. Okay, so we have this, and I want another list of random values. I just duplicated this by hitting Ctrl+D and then random seed, so you can see this is changing the values. I will be using pixel processor, but if you want, you can just use the RGB merge. Oh no, this one, RGB merge. RGB merge. So you plug this in R, this in G, and then we just provide B and A. So B should be black, A should be white. But I'm going to do this in pixel processor. We want the pixel processor to have the same resolution, absolute. This should be 0, and plug this one here, plug this one here. This should remain a color. The output format should be 32 bits. And the reason for choosing 32 bits is because we are going to allow a wider range of values, and we are going to allow negative numbers here to exist. So by default, you would have values from 0 to 1, But if you change this to 32 bits, then you're going to have like values larger than 1 and below 0. Okay, so in order to bring these things in, we need space coordinates. We're going to get the position, and then we're going to sample the first input image. So this is how we're bringing the first image in, and then we're going to bring the second image in. So image input 1, this is the second image, and we want to create a vector out of them. And then the output of this is either float 1 or float 4. So we can't right click and say set as output because this is a float 2. So we're going to use a vector float 4 and just use a float to here. So this is for the blue channel, we're going to leave it at 0, but for the alpha channel we're going to put out 1. So this is these two components are R and G, so red and green, and these last two components are green, blue, yes, red, green, blue, and alpha. Okay, so right now we have something like this, and I'm going to create an FX map node to read pixel by pixel the position in this list, and the FX map is going to draw a circle at taking every single position in this list. So for example, I'm going to press this I button here, so image information, and I want you to look at the R and G values here. So I'm hovering with my mouse this value here, which says R it's 0.3 and G is 0.18, and this means that in our FX map is going to place a dot at this position in space. So it's going to put this circle in X direction at 0.3 and in Y direction at 0.18. Okay, so let's actually do this. Going to the FX map node, I'm going to make it grayscale. I'm going to plug these things in. Just want to briefly check what is the resolution here. It's 124 by 124. It's good, we're working with the same resolution. And now going inside the FX map node, I want to make sure that we're seeing the FX map node. I'm going to choose a disk. I'm going to shrink the size a little bit, like 0.005 and 0.005. So we're having a point here. I want to remind that in FX map the 0, 0 coordinate is considered to be here in the center, but actually 0, 0 it's here. So in order to solve for this, what we're going to do is going to use this branch offset to reposition the point here. So minus 0.5 and minus 0.5. Okay, so now we moved the point here and we're getting something in every corner because tiling is activated. Now we're going to iterate, and we're going to iterate 256 times and set this one as an output, set as root, and nothing seems to be changing, but actually we right now have 256 circles sitting on top of each other here. And how we can convince ourselves that this is the case? Well, we're going to look at the FX map node, make sure that we allow the output format to show us values beyond 0 and 1. So we're switching this to 32 bits. And I just want to make sure the blending mode on the quadrant node is add. So right now every circle is 1, and if we have like 256 circles sitting on top of each other, you would see here like 256, and that's the case. Okay, but we want to read the positions pixel by pixel from this image and place the dots at these positions indicated by these textures. So we're going to select our quadrant node. We're going to go inside the pattern offset, empty function. We need to get the dollar number variable, which we can access it by with get float node, and from this drop down list menu we will choose dollar number. Divide this by 256. So this is starting from 0. It's a list of integers, starts from 0 and increasing by 1. Let me put a comma 1, then 2, then 3, 4, up to 255. Okay, so in order to make this from 0 to 255 to 0 to 1, we will divide this by 255. Okay, and now this contains a list of 256 values that are from 0 to 1. We want to make a vector out of this. We will input float 0, so in the y direction nothing is going to happen, but this is going to basically go step by step into this position and read them one by one. Okay, so with this vector we're going to sample our input. So this is actually our space coordinates. Okay, and we will use the space coordinates to read from this texture, and we're going to sample. This is how we read. We created the space coordinates that is going to step in every single position of this pixel and is going to read it. And right now everything is good. The only thing that we need to do is look here, and by the way I want you to be aware and look here every time to see what is the expected type of output. In this case it's float 2, this is a float 4. So how do I know? First of all, if I'm selecting it and want to set this as an output, I can't. This is grayed out, and you would know by the color of this output dot which type of variable this is. And in order to know which type is, you can just type float. So you can see like this is very light green is float 1, this more a bit saturated green is float 2, this kind of green blue is float 3, and this darker blue is float 4. So you can see this color from here matches this here. And we want to only extract the x and y component of this, which we can do with the swizzle float 2. So we can plug swizzle, we can plug the float 4 into swizzle float 2. Okay, so right now our FX map still has the points in this corner, but I think if we go here and set this one as an output, we now have every point in space according to the information that we're getting here. Okay, so I'm going to say, hey, this is initial state of creatures. Okay, and initial state of small creatures, and this is the initial state of large creature. Okay, now I want to show you how I think about setting this system of differential equations and how you can solve it. And by understanding this structure, I think you would be fine to make same or similar structures for yourself. Okay, so let me first of all bring a frame. I didn't want it to be here, somewhere in space, a frame. And I'm going to enlarge this, make it gray, so it's not very saturated, and try to make it larger, like so. And I'm going to name this animation frame. So this is one frame of our animation, and this is where we will compute from our current initial state. Okay, so from our current initial state, we're going to compute the next state, and this is, I'm going to name or categorize this as our first animation frame. And once we set this up, we're going to make a node out of it, and we're going to just duplicate this. Okay, so I will do something like this. Draw a wire from here and then hit the Alt button and make a point like this. Also, I want to bring the data, and also I want to bring the state of the small creatures. So let me have a look here. We have our small creatures, our data, and our large creature. Okay, and I will make a frame here and say this is our previous state. Okay, and then we will do a bunch of computation to arrive at a new state. And first of all, as you remember, these are differential equations because they involve derivatives. And we arrived at a point where we want to compute a derivative. And a derivative of a 2D function is going to be a vector field. And the interpretation of this is going to be every vector in this vector field is going to point an arrow to the direction of steepest ascent. And what does it mean? So if you imagine that you are climbing a mountain, then this vector field is going to show you at every point in space which direction you should follow in order to climb this mountain the fastest. A derivative is very similar with the normal map. So the normal map is based on the derivative, but it has some extra steps. Okay, and I want you can use, if you want, you can just use the normal map, and that would totally work. But I want to show you how you compute the derivative, and this has to do with bringing in the notion of approximations of functions and derivatives. And the most critical term that you need to remember is finite differences. So if you're going to go on Google and search how to approximate the derivative of a 2D mathematical function using finite differences, you're going to get a mathematical expression that is very similar to what we're going to use, and this expression is fast to compute and it works all the time. So again, it's an approximation, it's not the exact derivative, and at some point this kind of approximation poses challenges, but in most cases it works. Okay, so we're going to make a pixel processor node. We're going to input this here. We're going to say this is the derivative. Usually the derivative of a 2D function, and not only 2D function but higher order functions like 3D or 4D or n-dimensional function, is called gradient. So in Substance Designer we have these nodes which are called gradients, which are smooth transitions between values, but in terms of like calculus, gradient is the derivative. Okay, so how do we approximate this derivative with finite differences? So we need to bring our image in, or our initial frame or initial state in. So in order to do that, I'm going to get the float 2, this is the position, and sample the color. So right now we have our image inside of the pixel processor, and what we want to do in order to approximate the derivative is take some differences. So we're going to move the image a little bit left, and then we're going to take the same image and move it a little bit to the right and take the difference between the two, and this is going to make the x component of our vector, and then we're going to do the same but on the vertical direction. Okay, so how do we move things left to right? Well, in order to do that we need to add something. Nothing changed here yet, but if we bring in a float 2 here and change this value, you can see that we can move it left to right. Okay, so I'm going to also rename this. So if this remains 0, it's like this. If we change this, we're moving it to the left. So I will rename this left. Okay, then we're going to duplicate this, and this would be to the right. And I want to say, usually I am doing these things a little bit differently. I just want to show you this way because it's easy to see how I'm moving things left to right. What you usually do is move things just 1 pixel at a time. So I'm actually going to do this because now, as you saw how I move things left to right, you're going to know what I'm doing. I'm just going to duplicate or to delete those things, and I want to only compute the size of 1 pixel. So in order to do that, I'm going to take a float 2, make it 1, and divide 1 by the size. We're going to get a float 2, and in this case we're going to choose the size variable. So 1 is the entire image, and we're dividing it by the size, and size is 1024. 1 divided by 1024 is a very small number, which represents exactly an offset by 1 pixel. Okay, this is a vector. We only need we need just to sample the x component. If I'm going to output this, you're going to see how small this value is. It's, you can look here, it's 0.00977. Okay, we need to make a vector float 2, the x component, because we want to move this in the x direction. Okay, I'm just going to zoom in quite far and see when we're going to plug this in, you should see the image moving 1 pixel to the left. So be careful and watch closely. So yeah, it moved in this direction. Now I want to do the same thing but move it in the opposite direction. So for this I'm going to subtract. So we're going from the position, we're going to subtract this quantity, and this is going to move the image in the other direction. So you can see that right now moved into the right direction. So right. Okay, and now if we are taking the difference between the two, you will see something interesting. The result is kind of giving us something like an edge detection. So we're getting this value here. This is positive, and I want you to look at these values while I'm hovering with my mouse across the image. So it's right now it's 0.15, right now it's 0.00, and at some point when I meet the other edge,
and a sound system.
Sorry about that. When I'm meeting the other edge, you should see negative values appearing. Are they? They are not, because our pixel processor is not 32 bits. So change this to 32 bits. And right now if I'm hovering, you can see whenever I'm hovering around or on top of the other edge, we're getting negative values. Okay, so we did this for the horizontal direction. We now need to do the same thing for the vertical direction. So basically we will take our image and move it up and down and take the difference. Okay, so again, I'm going to, in this case, duplicate this. Now I want to change this and plug it into the Y component. I'm going to also use a 0 to plug it here and here, not to leave these slots empty. Sometimes you can leave them empty, but just to make sure, I will recommend that you plug 0, even though you don't want to change this, just plug 0 in. Okay, so this should be how we're going to move our image up and down. We're going to add, so our position plus this vector, it's going to take our image and move it up or down like so, and then we're going to subtract our position minus this vector, bring in the image with this offsetted coordinates. Yeah, so this is up and the other one is down. Okay, and the other one is down. And we're going to take the difference between these two, so subtract, and we're going to output this again to see that we're getting the top and the bottom, and we are going to compose this into a vector float 2, and then we need to again make sure what we can output. So we can output either float 1 or float 4. So this is a float 2, we need to make it a float 4, and we need to plug in another float 2 for those are the R and G components. We need to also put something for blue and alpha. So for blue I'm going to leave it at 0, but for alpha I'm going to output 1. Okay, so right now in this image you would have vectors, and vectors are arrows that are pointing in the direction of steepest ascent. So everything here is almost 0 because here we have a flat surface. So in our image here 0, it means it's flat everywhere, so we're not climbing or not going down the hill. But here at this edge, we're having a transition from black to white, and this is a gradient in which we are climbing the mountain, so to speak. And our vectors here are actually pointing, each pixel here, it's containing an arrow that points the most points into the direction of steepest ascent. So basically these vectors are perpendicular to our gradient. Okay, so good. Now we have our derivative, and we want to compute the next state of our we want to compute the next state of our large creature. And how do we do that? So right now we have our measurement, so this is the derivative, and which we measured, and after the measurement we measured the initial state, and after this measurement we get this vector field, which are directions. So we want to grow this shape based on the directions that we have. So for this reason I'm going to make another pixel processor node, and this is behaving like the warp node. So this is very, very similar to what the warp node in Substance Designer is doing. Okay, so we're taking the initial state, so I'm bringing this image in. I want to push this a little bit further, and I also want to change the sampling here from nearest to bilinear. So whenever we're doing this kind of approximations of growing shapes and things based on derivatives, it's good to set the sampling or the filtering mode of this node from nearest to bilinear. So we're going to grow and push things with values that sometimes might be smaller or larger than 1 pixel, and this bilinear is going to make sure that we're getting a smooth interpolation between pixels and things like that. Okay, so we just brought in our current state. We want to bring in our measurement, so we're going to sample the color. Also, I want to change the sampling, the sample color to be image input 1 and to be bilinear. I want to only use the x and y components, and I want to add this to my space coordinates and see what's happening. So we are looking at the result of this node, and once I plug this in, the shape should either shrink or grow. So the shape actually expanded. So this was before, this is now, so you can see it expanded. And what I really want, I want it not to grow this fast, I want to grow just a tiny bit. So for this reason, at this point I'm just going to place a constant value here. And whenever you multiply a vector by a number, it means that you are scaling that vector. Okay, so all the vectors here are going to be either shrinked or made small or large based on this value. So, and whenever you're multiplying a vector by a number, you need to use scalar multiplication. So you have this node, scalar multiplication. Okay, so right now everything went back to as it was before, because we are multiplying this vector by 0, which means that here we're adding by 0 and nothing changes. But if we now plug in this value and play with this value, you can see that this is controlling the strength of how much we push outwards. And I just want a small value here, like 0.05, something like this, even something less. Okay, good. So this is interesting because right now we managed to find a way in which we can grow our shape. But what we want to actually do is we want this thing to actually chase our small creatures. And what we are going to do is, instead of using a constant value here, we're going to use a map, an image. Okay, so how does this value is looking like? If I'm going to set this one as an output, you can see like this is a constant color everywhere in space. So this is why our large creature expanded equally in all directions, because we have the vectors that are pointing in all directions, but also in all direction around its circumference, but also we have this constant value that actually scales all the vectors in the same direction with the same magnitude. Okay, but if we are going to change this, like for example input a Perlin noise, you're going to get some areas growing faster and some areas on the edge growing slower. And we want actually to use this map here of creatures to attract or to make our creature grow in the direction of the small creatures. Okay, so how to do that? So of course we are going to use this initial state of small creatures, and we're just going to blur it a little bit. Maybe something like this, I'm not sure. Yeah, and I want to actually show you some tricks. So for example, using the blur node, you can see what effect it has. We can use the blur high quality, and this is going to give us a better result. It's much more circular. So what I want from this blur is to get this kind of effect, but I'm not getting it. So and I don't want to use this high quality blur because it's expensive. So remember, we are going to repeat this animation frame a few hundreds of times, and this is going to be it's going to become very slow to compute, because this high quality blur is expensive to compute, and multiplying it by hundreds of times is going to make things really slow for us. So I'm going to show you a few tricks. So the first trick is like a very cheap blur, is the transform node. So bringing the transform node in, and you can do something like this. Go into the MIP map mode, change it to manual, and then make one or two or something like this. And then you can duplicate this one and put it in here and put it in here. So you can see that we successfully blurred this 3 times, like the first blur, second and third blur. So you can do something like this if you want. You can also do another types of things. And probably this is very similar. Anyway, I'm going to show it to you. We can transform. You can shrink the size and then scale it back. So this probably is going to give you like very similar, if not exactly the same results with the MIP map trick. But anyway, I'm going to show it to you. So the output size, you can make it like 256 by 256. Go here and make sure the filtering is bilinear, and then you're going to use another transform node, and this time you're going to make it to bring it to the same resolution. And again, make sure that you are on the bilinear filter, so you can see everything is blurry right now. So shrink down and then shrink this up is going to blur things for you. But I think the way I did it in my example was, instead of choosing disks here, I think I chose paraboloids. So this will give me from the start a better thing. Okay, so I'm much more satisfied with this, and then I'm going to blur this with the chip blur and just make it. I'm still not satisfied. I wonder how did I do it here. So yeah, I think I remember, I think I changed the size of the blur to 256. Did I do that? I'm going to double check inside. Oh, so it's blur high quality that I used. Well, that's why it seems to be slow to compute. Well, yeah, just shot myself in my own foot. But yeah, the reason, yeah, still it's going to be a nice trick to show. I'm going to use the high quality blur, plug this in and shrink it down. So this is giving me a good quality blur. What I actually did is just decrease the resolution to 256, and then you don't need to use the transform node to increase it back, because I'm going to plug this one here. So remember, this node here is 256 by 256. This is 124 by 124. If I'm going to plug this inside here, so this is 256, but now sorry, not into the derivative. I mean, I need this here because this is going to be our growth map. Okay, so our large creature is going to grow being attracted by the small creatures, and is going to be attracted by this gradient that is around every creature. So I'm going to plug this in. Going inside here, I want to bring sample gray. I want to bring in the image 2, make it bilinear, and set this one as an output. And now if we look at this, you can see that we took our 256 image and rescale it to 124. So basically the rescaling is automatically doing when you're using this image inside this image, or inside this pixel processor, which has a larger resolution. Okay, so now I want to go back here and see how our large creature expanded based on this, and I want now to replace this with this, and you can see we're now getting something different. So you can see we're having this without this map and with this map. Okay, so I want to still take this and multiply this by a value, because I want to still have control over how much we're pushing things around. So you can see what the effect of this is, and I think I'm just going to put this like 0.1. Okay, so this is how my creature is growing. This is the current state. Good. And now what we want to do is we want to take we want to update the positions of our small creatures based on how the large creature is growing, and then making sure that the small creatures are actually running away from the large creature. Okay, so it's going to become interesting because we're going to use the data to look into this map and pick the directions of this vector field in order to understand which of the small creatures are close to our creatures, and if they are close to our creature, in which direction they should run. Okay, so I'm going to use a pixel processor, make it the same resolution as this because we're working with data now, and we are going to update the positions. So taking the positions in here, changing the resolution to 56 by 1, making it 32 bits. Okay, we're going to get the float to read these values. So we're going to read them, sample. Okay, so right now we just read this value, so we have the same values that we have here, we have them here. But what we want is actually look in this space with this position and pick the normal vectors that are in this space. So this is a really crucial thing to understand. You can use this texture which contains position, so those are texture coordinates, to sample another texture, and this list here is going to be populated with whatever value happens to be in this space according to these values. So this value here, if you remember, it was like 0.3 and 0.18, which is 0.3 in x direction, it's like 0.3 maybe around here, and 0.18 is going to be around here. So this pixel, the first pixel here, should be black because it is looking into this space around here, and it's reading what is the value of the pixel here. It's black. Okay, so what is going to probably happen is probably we're going to get everything black here, or maybe if we're lucky a few pixels are going to be colored, because our creatures may not be very close, or probably none of them, and we're going to actually look at this. I need to make a blend, so I will convert these creatures that are black and white, I'm going to convert them into a color image, and I want to just blend this with this and add them together. Okay, so it seems that we are going to have maybe 1 or 2 pixels that are going to be colored. So at these positions, at this and this position, somewhere in our texture, we're going to get a color pixel, and everything else is going to be black. Okay, so these are our space coordinates. And we're going to look with these coordinates into our larger map and pick up what are the vectors that are pointing in the steepest ascent. Okay, so these directions are we're going to use these directions from here in order to update the position of our small creatures. So I'm going to bring this here in and sample, and this is image 1, and I'm going to leave here this one as is. Yeah. So you can see we have one green pixel, everything goes almost black, and maybe, yeah, we have another maybe orangish or brownish pixel here. So if you remember, those were like the two things that we have. I want to rename this, so by the way, this should be 32 bits, and I want to rename this, and this is going to be how should I name this? This is velocity vectors. So another thing that I want to take a moment and talk about is whenever you're updating a position of something like a particle, you have the position, and in order to move it, you're going to add a vector to it. And usually this vector that you use to move the initial position of the object to the next position, you're going to add position with velocity to get the new position. And that's why you usually name these velocity vectors. Also, it's quite common and depends on the situation, but it's quite common when you are taking a derivative, the vectors basically can be named velocity. So you have position, the derivative of position is velocity, the derivative of velocity is acceleration. So whenever you're taking the derivative of a function, you can the first derivative of a function, you can encounter this, or you can find yourself hearing it named either gradient or first derivative or velocity. It's almost the same thing. If you are like super precise, these are not the same thing, but some people use them interchangeably. And in this case, because I want to update the position of our creatures, and I'm going to add these velocity vectors to our position, it makes sense to name these vectors velocity. Okay, so in this pixel processor here, I'm actually sampling the vector field given by what the creature is doing, in order to tell, hey, this is where the creature is, it's pointing in this direction, you should run far away from it. Okay, so in order to do that, I need to right now update the position of the tiny creatures. So I'm going to make another pixel processor, make it the same resolution, 256 by 1, make it 32 bits, plug in the position, and then plug in the velocity vectors. Okay, go inside. We're going to read the position first, which is the first input. So this is the position here, this is the velocity here. So sample color, this is position, okay, and then we are going to duplicate this structure here, and in this case we're going to sample image input 1, and this is the velocity. Okay, we're going to multiply this by a number because we want to control the speed, or how fast or how long these vectors are, and by the length of these vectors we're going to control how much the small creatures are moving with each frame. So in order, if you remember, we have a vector, we need to multiply it by a scalar, and then we're going to just plug a number, like for example 0.05, and this might be a positive or a negative number, and it being positive or negative is going to change the direction. So if it's positive, it's going to either the tiny creature is either going to run away from the large creature or towards the large creature. So right now I can't figure out which is the direction in which it's going to the small creature is going to run in. I assume it's going to go towards the large creature, because if you remember, our derivative is computing the steepest ascent, which means the vectors are pointing from dark to white, which means all the vectors are pointing towards or inwards into the creature. So probably a negative value would push them away. Okay, something like this, and then we need to add. Okay, so we have current position, here. Here we have scaled velocity, and here we have the updated position. I mean, this is like previous, not current, previous position, scale velocity, and this is the current. So in this frame, the tiny creatures are actually moved into this current position, and we need to output this. And remember, always look here, we can either output a float or a float 4. So float 2, so we have here the RNG components, and we need to output the blue and A. Blue is going to remain 0, A is going to be 1, and set this as an output. So now this is the list of the new positions, and we need to draw the new particles now. So I'm just going to copy the creatures, I mean particles or creatures interchangeably. This node, it's reading a list of positions, and then it's drawing these things. So I'm going to duplicate this node, and I'm going to just plug this in. I want to look at this and see if something moves and changes. So these are the previous positions, and now if I plug in the new position, I think maybe if we remember, kind of two small creatures should move. Maybe we can see them. Yeah, so one was here, so previous position, yeah, two creatures, I think this and this are moving. So right now they are not moved, and right now, yeah, this and this, and they actually moved away, which is really good. Okay, so at this point we computed current state, we computed the new position. What we can do is, let me think a little bit. Yeah, so I think we are able to output things. I'm going to draw a wire from here to here. I'm going to also draw a wire from here to here. So you can see the linearity of things. We took in the previous state of the creature, and then we computed the current state of the creature, and we're going to output this. And then here we took in the previous position of the creature. We compute the new position of the creature, and we output it, and you can see how things are following the same linearly, such that what we bring in, we also output out. Okay, and there is one other thing that I want to make, and this is more like an effect that I want to show. If I go back here and show you at this output, you can see that the particles that are moving, they are leaving this trail, and I think this is an interesting effect, and I wanted to replicate this effect. Okay, so going back here, and how did I do that? Yes, so I'm going to, what I think I did is put a transform node. I mean, this, it's acting like a blur node. So I'm taking the input creatures and I'm blurring them a little bit. So I'm in the transform node. I'm going to manual MIP mode and take this to MIP map level 1. Then I will blend things a little bit, output this here, make it like so, and then just decrease. So I will add things together, maybe not add, just leave it as a copy. I think, did I add them in the previous? Let me check. So I think here in the way in which I set this up, I think I'm adding things together. Yes, so this blend mode is add, which is interesting. I'm going to also use the same add here. Okay, so the blending mode will be on add. It can also be on copy. I will make it on add, so you can see like everything become way brighter. And I think I use like 0.99 or something. Let me check. This is not super important right away to use the exact same values. Anyway, I'm going to try to replicate this as close as possible, so I will copy this value from here to here. So it's this. Okay, and I will output this. Okay, and I just want to name things. So this is this is the previous state of the large creature. Okay, this is the previous position of small creature. Okay, this is this is the initial or the previous trail state. So in this system here on this line, we're going to update the trails of our small creature. So those creatures, while they move, they're going to leave a trail behind. So this is the previous trail state. And initially, because it makes sense, because those creatures, this is their initial position, they never moved, they don't have a trail, but while they start to move, they're going to blur with each iteration. So this system is like really cool, and I think the more you think about it, the more you would understand it. And right now you think like, hey, nothing happens, but actually it happens. So while you progress in time, you're going to take this input here, which is going to accumulate particles, and then because we are blurring them a little bit, the trail becomes blurrier and blurrier. So that's why you're getting this effect here. So the ones that move, you can see that right here they are very sharp, and then they become more and more and more blurred. This is because this system here in which I set it up, it's cumulating and progressively adding more and more and blur. So those are from the past, so those are like the position creature here was super sharp, but as time passed, creature moved, and this creature that was here became like blurrier and blurrier and blurrier and blurrier, and that's why you're getting this kind of cone. Yeah, so this is a little bit mind-bending to think about, and I really suggest you would make a few of these nodes until you get how things are updated. Okay, and the last thing that I want to output, so you can see here we're outputting how our creature is growing, we're outputting the current position, we're outputting the trails, and in the end we're outputting the creature and the trails together. So you can see that, hey, this is our creature, it's growing and chasing the small creatures, and then you can see them overlaid on top of each other. So the final thing that I want here is just to make this a little bit larger and add, we're going to use another blend node, and we're going to add, so I think I will do something like this. And add this here, add, and then just change the, yeah, I think so, yes. And this is my last output, and I'm going to also comment this, make this here another in output. And I really want you to look at this and understand that this structure is very important to understand. We have previous state and then current state, and this is how we're actually pushing and integrating our differential equation. So whenever you want to solve a differential equation, you solve it by taking an integral, and integral, it's actually accumulating all these changes over time, and this is what we're doing here. And whenever we're using this algorithm of forward Euler, it's actually growing or pushing the system forward in time, frame by frame, and that's why you would want to be very organized and systematic of this. So we're bringing in the previous state, we made some computation, some measurements. If you remember, the derivative is a measurement of the current state, and then based on these measurements we make some actions and take some decisions, and then what we want is we want to output the current state, and then when we repeat the same thing and we do the feedback loop, then the current state is going to become the previous state, and so on and so forth, and we repeat these cycles over and over again, and we construct our movie frame by frame. Okay, current state. And also, I know this might be probably a bit tedious, I will however rename this once more. So current state of large creature. So in this current state it meant that it grows, it's growing a little bit and chasing the small creatures. This is our current small creature position, so I want to rename this current small creature. Okay, so I think did I? Yeah, I think I made a few copies of this and I'm not entirely sure why or where, so I'm just going to copy and paste this. Yeah, apparently it doesn't want to do that, or maybe I'm not just seeing it. Oh, I want to put a comment here. Yes. And this is, by the way, I'm going to comment this as well. And this is the current small creatures drawing. Okay, and I want you to notice that whenever we're working with data, so here we updated the positions of our creatures, but then we need to draw them. So we will use this technique many more times in the future in other tutorials when working with data. So we updated the data, but we also need to draw it. And you will also find this paradigm where we have like two nodes. One node is where we compute the data, and those are basically small textures with pixels like this. So this can be regarded as lists of pixels or lists of values, and then we will have another node that it's reading these values and then draws things based on these values. Okay, and this is our trail, our current trail. Okay, and the last thing is our current drawing, our current entire drawing. And probably you can come up with better names than me. Okay, so I think at this point we are good to go. We actually created the way in which we solve our first frame. So if you remember our first frame of animation, if we remember, we started with this state here, and then we evolved this state a little bit, and there is a small difference, so previous and current, so you can see things are changing here a little bit. Okay, and the last thing that I did in my other setup is I think I put here another transform node which is blurring things a little bit. So what you would notice is in time this current state here, our creature, loses its blur here, so it's going to increasingly get sharper and sharper here. So I will put a transform node that is going to I'm going to change the MIP map value of that transform node in order to blur things a little bit, yeah, in order to, with every frame at the end, after computing the current state, we want to blur this a little bit. And the reason for blurring this is because when we compute this derivative or this measurement, it's very nice to have a smooth gradient to compute this derivative on a smooth function. Okay, so that's the reason why we want to blur this in time. So right now what I will do is take this entire thing, right click and create graph from selection, and I will rename it for short anim frame. So the reason for doing this is because I already have a node here which is called animation frame. You can rename it however you want, but it makes sense. This is like an animation of a frame, so I just rename it like anim frame here for short. Okay, good. So this is again one crucial point to be careful, because sometimes things change and you will not get like the same results. And I'm going to drag this in here and going inside, and we need to make 3 inputs. So input grayscale. Okay, so this is the input of our creature, is going to be plugged in here, and then we're going to input color. And crucially, what I really like to do is make sure that all my input nodes match the type of node that is going to be inside. So for example, this is going to be plugged in here, and it has to be 256 by 1 and 32 bits. So I'm making sure that this one it's meeting the same, or it has the same properties, so output size. Okay, the resolution is good, and I want also the depth to be exactly the same. And then I just want to input another grayscale, and this is the trails of our small creatures. Okay, and then just output 3 nodes. And here you can leave them by default, because right now they are going to automatically adjust. So this is going to inherit the properties from here, and this is going to inherit the properties from here, which is 256 by 1 and 32 bits. This one is going to be correct as well, and this one. Okay, so I think we're good. And yeah, I don't want one thing to happen. The FX map node here, I don't want it to be 32 bits, because you can see here that this blend node it's also 32 bits. And what happens, because this is on add and we are keep adding things to it, those values are going to increase quite a lot, and I don't want the small creatures to become like brighter and brighter and brighter. So this is 32 bits because this is 32 bits, and I don't have a reason for this to be 32 bits. The reason it was 32 bits is because in the beginning I wanted to show you that all the creatures were sitting on top of each other. So for this reason I will make this 16 bits, and also this one here is 32 bits and I want to make it 16 bits. Okay, so we have our animation frame and we are ready to plug things in, and then we're going to actually run the simulation and see how things evolve. So plug in the large creature, plug in the data or the position, plug in the trails. Okay, so what happened? Why don't we see anything? Oh, what we're seeing is by default Substance Designer is showing the first output here. So here we have the data, here we have our particles, and here we have the creature plus particles. Okay, good. And now we're going to duplicate things together, and you just plug the previous state into the current state, previous position, previous trails. Okay, and I want to look and see if things change. So this was before, this is after, so you can see that it's the large creature is starting to grow, and we can actually see what's happening. So you can see that the large creature is actually chasing this small creature here. So right now, okay, and another interesting thing, you don't need to actually duplicate one node at a time. So right now you have 2 nodes, duplicate 2 nodes and make the connection, so like this and like this. Okay, now you have 4 nodes, duplicate 4 nodes, now you make the connection, so you can see how our creature is growing. And then you have 8 nodes, duplicate 8 nodes and make the connections, make the connections, make the connections. Okay, so you can see how our creature is starting to grow. And one thing that I don't like is you can see that we're getting this kind of noise here, and this is probably because our creature is growing too fast. or because I don't put the blur at the end, so we will see. So right now I just duplicated these nodes, and I hope designer is not crashing. It didn't. By the way, be aware that when you're doing this kind of stuff, depends on the day. Sometimes Substance Designer has issues. Of course, there would be a reasonable explanation, but sometimes it seems that there is there is none, and you just find Substance Designer starting to act crazy. Okay, so you're seeing actually like how I'm duplicating nodes, and the number of nodes grows exponentially, and I'm just making a few number of duplications. So right now I will have 64 nodes, and the number of duplications that I used is, I don't know, maybe 5 or 6. I think 6 duplications. Yeah, so the number of nodes grows exponentially, and hopefully designer is not crashing. Maybe this recording is a little bit long. Okay, so designer just crashed, and now we're back in. So where we left, we were trying to duplicate this sequence of nodes. So I will do just that. I'm hitting Ctrl+D to duplicate things around. Okay, so we're going to again plug this here, and plug this here. And we want to look at the last iteration. And we also want to look at our tiny creatures to see what they're doing. And yeah, it seems like they're leaving trails, but it's not very bright. So I'm wondering why. Maybe was this a 32 bits here? So you can see here I have a very bright trails, and I wonder if this is not 32 bits somehow. No, it's 16 bits. Oh, why? 995 add. Yeah, let me double check. Why are not my trails, the moving ones, why are they like this? Adding 995. Yes, still it's a bit strange. Oh yeah, some of them, yeah, so some of them are behaving accordingly, yeah. Oh yeah, that's why. Okay, good. And I think the way in which I will solve this issue here of smoothness is just going to add a transform node on the creature in order to blur it a little bit, and then I will blend it in order to control how much this blurring what is the effect of this blurring. Okay, so I'm going to go here, and here I will try and put, yes, here I will put a transform node. Okay, and then go here into map manual, put this to 1, so this has blurred a little bit, and then I will put a blend node, and I want to have another look here to see how I did it, if the blend node is on add or just a copy. So this is the transform node with 1, and then the blend node is on copy, and opacity is 0.15. so this is the contribution of the blur here is just 15%. Okay, so go in any or in either of these. The transform node goes at the top, this goes at the bottom, copy, and then we're just going to 0.15 and plug this in. So yeah, it seems to solve some issues, but they are continuing here. Okay, so solving this would actually have to do with maybe with this value here. Yeah, this is having an effect as well, maybe like so. And also I want to play with the speed in which these things grow. 0.1, maybe it's too much. Yeah, maybe 0.05. Okay, so our particles are basically running away, being chased by the creature. I'm going in the drawing to just decrease our creature opacity a little bit, so we can see how it's chasing the particles. Okay, good. So we're having this system, and we can do another thing in order to avoid a very difficult to manage graph. We can once more pack this thing into another node. So I will take this and right click and create graph from selection, and I will rename this 64 anim frames. Okay, hit OK. Designer is probably going to crash again. I'm upsetting designer with this kind of stuff. So probably the recording is long, and maybe the memory and stuff like this. I'm going to stop it again and come back when designer is coming back to life. Okay, so I was able to select everything and create a graph from selection, and I right now can delete this and bring this thing here. So I named it anim frames 64. I will go inside and make 3 inputs again. Input grayscale, input color for our data, make sure the data is matching our resolution, and our bit depth 32 bits. Great. And then our last input, another input grayscale like so, and then our 4 outputs. So our current large creature state, our current small creature position state, our small creature current trail state, and our entire drawing current state. Great. I'm going to save and go back here, and now we just want to input our data back in. So our creature is the first input, our data is the second, our trails is the third, and now everything seems to be working good. Okay, so we're now duplicating 64 frames at a time, and our simulation is evolving. And you can see how it was before and now how it's after. So you can see we're getting this interesting behavior where our creature is branching in following these three small creatures. And duplicate this again. Yeah, I really like what's going on. So you can see how this is growing. This is after 64 iterations, and another 64 and another 64. Okay, so I will do a couple more of this. I really like the drawing that we're getting. It's actually a bit more interesting than the first one. Yeah, kind of cool. So, I mean, all in all, seems to be interesting and nice. You probably imagine like, hey, this is not like super useful, I can't get it, I don't want, for example, to see all this. It would be, for example, cool if this was more sharp and things like that. So you can go inside and play with the parameters, like for example with the speed of how things grow, and you're getting a different result. So you can blur things a little bit and stuff like that. But what I want to say is that like the main idea is creating I mean, first of all, we were talking about partial differential equations and how to solve them, and in order to talk about like super heavy math and stuff like this, what I want you to understand is that this is how you can simulate them. You're starting with initial conditions, which in our case was this. So we had our creature and we wanted to eat some small creatures, and then we want this data that it's our creature's position, and we use this data to control the position and update the position of our small creatures, and they want to run away from the large creature. And then we also draw this in order to make the trails. So what I want you to understand is that for this system, in order to work, you only needed you only actually need these two pieces of data, like the creature itself and then the positions of the small creatures, and you need to draw them. The third input that we are updating is just for creating this trail effect, which I really like. But this has and contributes to the behavior of this entire system, but not too much. So previously, when I created this system, I didn't use the trails, and I was getting a similar kind of pattern, but I just like it more with the trails. And also I think adding these trails, it's kind of interesting to see that, hey, this could be like ants, and ants actually are known to leave like a scent or a pheromone behind that other ants can follow and track and things like that. And what I want to reiterate again is you don't know, or you don't need to go and learn about the math and things like that. You can just go and use this kind of setup where you make an animation frame. You're taking an initial condition or an initial image, and you want to update it somehow in order to produce a new frame. And this process is called like the feedback loop, where you are taking an image or a current or initial state, you do something to it, and then you output the new result, and then you take this output result and repeat the same operations again to this new outputted result. So you basically duplicate the nodes that is doing all the operations, and you're getting a new thing. So this is going to make like things super complex too. And I want to show you another really quick example to show you what I mean by feedback loop and how it's producing complexity. And remember that we're getting complexity here from two processes, one which is the feedback loop, and the other is the connectedness or the coupling of the interaction between the two systems together. So we are making the small creatures interacting with the large creature, and this collaboration or this connection between them is giving rise, and it's producing I can't remember that term. Yeah, so this is producing emergence. So you're getting a more complex pattern or behavior from this interconnection between two systems. Okay, so very quickly I want to show you something else, and probably you're aware, some of you may already know about this. I'm going to take a line, I mean a shape. Okay, I will make a narrow shape like so, and I'm going to take this and transform it. So this is the input. I will take this one and move it and rotate it. Okay, and then I just want to duplicate this stuff and rotate it in another direction like so. Blend these things together, add the two together and make them like so, and I will add this is the initial state. I will add the initial state to the things that we modified. So add these things together. I will make them like so. I also want to resize this transform node a little bit. It's starting to tile. I don't want this effect for now, so I will do it like this. I also want to shrink this again, also disable the tiling. So make something like this. Okay, so we take the initial state, we're doing some operations with it, and then this is the output. Okay, so what we want to do is take this output and plug it in back into the same function. So we can't do this in Substance Designer like so, but we can do it by just duplicating this, okay, and plug this output here. So this is now the output and this is the input here. So look what's happening. And if we are duplicating this again and plug this in here, look what's happening again. Okay, so in order to do this, to do it like this, I just want to actually make another node, select everything, create graph from selection, and rename it like feedback loop. Okay, hit OK. This is our feedback loop node. I don't need this anymore. Just delete them. Go inside, put an input, grayscale, like so, and an output. Okay, so this is after the first iteration of the feedback loop. Second iteration, duplicate things more. So we're getting this now. So yeah, this is a fractal, and this is like iterated functions or feedback loops. loops, and they're giving you this kind of result. So if you go now inside of any of these and change things around, you can actually change the entire thing. Yeah. So you can do a lot of interesting things with that, and you can see how complex these things can become. And you can go, for example, here and just decrease the opacity of this node, and you can see what's happening. Or you can go here and decrease the opacity and get a different result. So yeah, feedback loops actually give you tons of interesting stuff and complexity. Okay, so in the end what we were getting is this kind of system of particle or tiny creatures running away from a large creature that wants you to eat them. And I think this system is interesting and nice, and it's looking natural. So the reason the reason this is producing natural looking effect is because it's replicating or it's mimicking something that actually happens in nature, and that's why, because we are mimicking this process, we're getting something that's looking inherently natural. Sorry. Okay, so the last thing that I want to show you is how to make an animation. So what I want to do is, I think I like this state. I like the transition from here to here. I will delete these two nodes here. So we pushed in time our differential equations or difference equation a few frames, and now we want to export this as a sequence of images. So right now I don't want to push this system in time 64 frames at a time, but I want to push them one frame at a time. So I will do the following. Animation frame, I'm going to take this one and plug things in like so. Okay, so this is the previous state. I'm just going to zoom in. This is the previous state and this is the current state. So you can barely see a difference, previous, current. Okay, so this seems to be like the simulation. It's advancing in time slow or too slow, and we, in order to make a movie that captures some interesting or some large movements, it means that we need to export a lot of frames. And we can do a trick here. If you're familiar with solvers and things like that, you would have a concept that it's called substeps. So you would do something like a nesting. Inside of an iteration, you would nest a larger number of iterations. So as kind of how we did here, we nested 64 iterations inside one of these. So here we can think of like, hey, we have 1, 2, 3, 4, 5, 6 iterations, and inside of each of these 6 iterations we have 64. So if our animation is not moving very fast, we can actually make this trick. We're going to nest a few iterations inside of another node. And for example, I am going to try 10 iterations. So I'm going to duplicate this until we have like 10 frames. So 2, 4, 8, and then another 2. Okay, so I'm going to take this bunch here and make another node, and I hope designer is not going to crash. I'm going to name it 10 anim frames. Please don't crash. Yeah, it didn't. I can delete this, bring this in, put inputs, input color, and then make it the appropriate size and appropriate bit depth, and then another input grayscale like so, and then all four outputs, 1, 2, 3, and 4. Great. So now this is pushing our simulation 10 iterations forward in time, so I think we should see a bit of more advance from the previous to the current, so we are advancing something. Okay, so in order to export things now, I'm going to put an output node here, and I'm going to leave this here, so this is just output. I'm going to leave this blank, and then I'm going to output this one, so you can see this is output 1. And this is interesting because if these outputs are named correctly, then you can very easily import them into software, like for example in After Effects, like an image sequence. So I usually take, if this was named output 0, that would make sense, but because it's output just like that, I'm not going to use it in After Effects, so it's not going to I'm going to export it anyway, but I'm just going to delete it from the folder, and then when I will open After Effects and point After Effects to the folder here, it will automatically detect the image sequence. Okay, so this is the first frame that is going to be exported, and right now I'm just going to duplicate things like this and plug this and this, and I mean like this and like this. So you can see by default this right now is output 2, and there is a difference between output 1 and 2. And now you can use again the duplication trick. So duplicate 2, and those are named correctly, and they are actually continuing to grow, and then you can take 4 and duplicate them and just connect them once, and everything else is correctly connected. Okay, so right now you have 8, and then duplicate 8, and you have now 16 frames. Okay, so our animation is growing from here to here, and then you take 16 frames and duplicate them, and you already will have 32 frames. Okay, so here, and then take the 32 frames and duplicate them once more, and you have 64 frames now. Please don't crash. It didn't. Okay. So the last frame, it's 64, and our system advanced quite a bit. And right now what I'm just going to do is hit this button here and export outputs. Okay, so I'm just going to point this to the correct folder that I want, choose the the type of file that I want, and then just hit export outputs. And this export is going to be very fast, like maybe a second, a few seconds, something like this, and you're just going to have all the 64 images exported into your folder. I usually export maybe around 300 images. This can be like 10 seconds of an animation, so I just make like 3 exports and things like that. So yeah, I think this is it, and I think this is a like an interesting definitely an interesting idea to try and make, and I really encourage you to think of this system. You're creating a node, you're putting instructions, and then you repeat the same procedure multiple times, and this is called feedback loop. And once you have it in this form, remember that you can go inside and just tweak things around, and you will get like different results. So this is, you build the system like this, and then you just go and play with the parameters, and you will definitely discover like super interesting things. So that is where the discovery actually happens. So right now that I have the system in place and I know it's working, I can go inside and change the parameters and see what happens. So I can go here and see like, hey, my growth map, is it like too blurry or not too blurry? What happens if I'm changing the blur here? So you can see what changes. Okay, so maybe 4, I don't know, maybe this is too much. So then go and change other things, like for example the strength, so the speed with which our small creatures run from the large creatures. So right now they are running away with this kind of speed, but what if we lower this speed 5 times? What happens? So definitely something different. Okay, you can see like you're getting more like branching like this. So, and then you can add other nodes, or you can change this trail parameters, and you're going to get something different. Okay, so I think 9.5 it's looking good. Yes, and I would suggest you to try and do more simple systems in the beginning. This one is fairly complex, so you have an interaction between 2 systems, and you're computing various stuff, and you also have like kind of interesting and new ideas that you might not be familiar with. For example, this idea is really cool, like sampling from this space where we have the derivative of the creature, large creature state, and we're sampling it in order to get how to update our small creatures. This is like a super interesting idea. And then updating the position with velocity is another interesting idea. And then how you go from data to actually drawing the stuff. Yeah, so fairly interesting stuff. And also another critical thing to do is how things are actually interplaying with each other. Because for example, right now if we are looking at the growth map, you can see that the growth map not only contains the small creatures, but also contains the trails of the small creatures, and these trails are actually influencing. So the creature, the large creature, not only follows the direct the small creatures that are very close to it, but also started to follow the creatures that are leaving a trail, because those creatures leave trails, and the large creature now has access to this trail and actually can use this as the growth map in order to move around along this trail. So the system is becoming like much more interesting because of this way, and the data flows into this graph in some interesting ways. So I would suggest you would just play around with systems from simple to more complicated, and just try to make it make more sense to you, and not necessarily thinking about like, hey, what is the derivative? If you don't want to think about derivative, just use a normal map. And if you want to update, for example, the current state here, like so, don't use the derivative. You can use like the warp node, but you need to actually play with the you would need to play with the values until you get something interesting. So yeah, I think this is it, and I think this is a really interesting technique, and it combines several ideas in which we're using pixel processor and fx map to draw things and to extract data and to sample. So yeah, you have plenty of things to think about. I hope this will be useful for you. I will be more careful with the time. Again, I'm trying to improve the quality of my tutorials, but in the meantime, it is what it is. I really hope this is helpful for you, and I hope I will be able to improve the quality of them and be much more coherent and make the tutorials shorter. Yes, so if you like the tutorials and if you think it's worth, please share it and let people know. But in a way, I feel a little bit embarrassed about the quality of it. So yeah, if you don't think this worth be sharing, please don't do it. But I don't know, spend the time trying to understand the ideas, because those are new ideas, and those are ideas that can be actually practical for you. And if you manage to understand them, you will be able to make stuff for yourself, which is like really critical. So you would have freedom of creativity, not only in the technical realm, but also you'd have freedom of creativity into making new artistic stuff. So yeah, thank you very much, and see you next time.